Hello, my name is Sahil Kirangi, and I'll be presenting my lab 2 for physics, specifically on projectile motion. So to introduce, in this lab, we basically analyzed the motion of an object in both the x and y axis, and we looked at its projectile motion. So I go on to compare the observed movement seen within the computational model for gravity and the computational model for gravity and drag. In this case, the object I used was just a paper ball, and then I used Tracker for the object's observed position and GlowScript for the code for the computational model of the object. Fundamental principles used in the lab, we just used Newton's second law, the momentum principle, which just defines net force as the change in momentum over the change in time. Gravitational force, we used that with the negative downward force. So the force from Earth and the ball pulling each other is at equal magnitudes. And then we also used drag force, which basically just says the resistive force is opposite of an object's velocity. So this is my observed position on Tracker. As you can see, I just observed markers showcasing the ball moving downwards. That's all that was. Now for the computational model, which is only gravity, I basically defined just the net force to be the net force, just the net force to be the force of gravity. So we just have that negative net downward force. I made just the regular velocity update and position update formulas over here, so as according to the momentum principle. And then I created the arrows in the model that defines the gravity and velocity. Notice over here I don't have arrows for drag because drag is not included in this model. Next, as the graphs for the first model, I looked specifically at the x-axis and then I looked at the y-axis and I compared both the observed on Tracker and model 1, which is just gravity on GlowScript. As you can see, they basically show very similar results. X-axis is very linear, as the object is moving linearly in the x-axis, while in the y-axis it's moving in terms of a parabola, which makes sense. That's parabolic. That's how it should be. Now in our computational model for gravity and drag, you can see we now include the drag force formula right here. And in terms of our net force, now we have to add both the gravitational force and the drag force. Now the next new thing we have is we define the arrows for the drag force acting on the ball, and we also state that drag force opposed to the velocity, as we know. Now what I did was I compared the observed thing on Tracker, the observed model on Tracker, with model 1 and model 2, both on GlowScript. So I have all three of the arrows pointing down and they all show similar results. Again, we have our x-axis being linear and our velocity, we have our position for our x-axis moving linearly and our position for our y-axis moving in a parabolic fashion, which again makes sense according to how the net force is acting. Now, possible errors we could have had are clerical errors. So when I was tracking the ball on Tracker, I could have made errors in terms of how I dispersed the ball. Maybe my ball tracking it wasn't as accurate as it should have been. That does cause some small errors. Next, our ball mass, which wasn't evenly dispersed because we used a paper ball. So our computational ball may not have been able to completely predict its path of motion, specifically in terms of how the net force was acting on the ball. Also, I guess a third thing would have been the fact that the ball had a lot of, in terms of our graph and our data, a lot of the data was simplified, so maybe that would have changed our results by a little bit because I was rounding some of the data points. Now our takeaways, so with model 1, we had just a linearly increasing velocity, just linear, and our model 2 shows that the velocity slowly begins to decrease. We can see the change in velocity gets smaller and smaller. Particularly, this is because of our drag force. So at some point, model 2 would depict the terminal velocity, reaching terminal velocity, because at some point the velocity would be just getting parallel to the x-axis. And at that point, that can be considered the terminal velocity. Now, what if the object was thrown up? So the time taken to reach the ground would be longer, as our observed motion model only took around 0.36 seconds, while as if it was thrown straight up in the air, it would take around 0.45 seconds. So this aligns because the overall displacement in the y-axis would be larger, and so gravity would take longer to slow down the velocity to 0, as in bring it back down to the ground completely. And that is it. Thank you guys so much for watching.